right now, if you step on the accelerator of a high-performance EV, you aren't just, opening a throttle body like in an old gas car.
Right, yeah, it's completely different.
Yeah, you are initiating the sequence where the electrical components inside the motor are subjected to voltage spikes so violent they literally try to tear the atoms of the insulation apart. And at speeds, a million times faster than you can blink.
It really is an invisible war zone in there.
Exactly. And if those atoms give way, the resulting short circuit has enough localized energy to turn the inside of the motor into liquid slag. So today, we are exploring that war zone inside a modern dual motor power control system, or PCS.
Because it is a completely different paradigm of failure than what we're used to in internal combustion engines. We are dealing with an environment where catastrophic destruction isn't measured in minutes or seconds. It's measured in microseconds.
Oh, absolutely. So welcome to the deep dive. We've got our hands on a highly technical engineering document detailing one specific, just devastating failure in an electric vehicle.
Right, a motor winding short circuit.
Yeah, which our sources classify as fault A03. But more importantly, we are diving into the, frankly, incredible engineering required to stop this fault from destroying the vehicle while you're actually driving it.
Which is a huge engineering feat.
Right. And to you listening right now, whether you're, I don't know, an automotive engineer or just someone who drives a modern EV, this is a masterclass in how complex, high-stakes systems manage catastrophic failure. We're looking at extreme physics, the brilliant software designed to contain it, and the ruthless testing required to prove it works.
Yeah, and to really understand the gravity of this, we have to look at the automotive safety standards first.
Okay, set the stage for us.
So safety is categorized by different integrity levels, and what we are discussing today falls under an ASIL-D safety architecture.
ASIL-D, that's the top tier, right?
Exactly. That is the highest, most stringent classification for automotive safety. And under that ASIL-D architecture, the engineers are bound by a strict parameter called the fault-tolerant time interval, or FTTI.
Okay, so the amount of time they have to tolerate a fault before things go bad.
Right. And for this specific winding short-circuit fault, the FTTI is less than or equal to 60 milliseconds.
60 milliseconds. So to put that in perspective, a human blink takes about 100 to 250 milliseconds.
Yeah, so less than half a blink.
The system has less than half the time it takes you to blink an eye to detect a massive physical failure inside a motor spinning at thousands of RPM, calculate a complex mathematical response, and execute a safe shutdown before the vehicle's electrical architecture is compromised. That is wild.
It's precisely what they have to do. And to understand how it does that, we really need to map out the landscape. We'll be moving through 5 dimensions today.
Okay, lay them out for us.
First, the root cause analysis of the physical breakdown. Second, the hardware and software diagnostic race against that 60 millisecond clock. Third, the design failure mode and effects analysis, or DFMEA.
Which is basically how we engineer the hardware to resist the failure, right?
Yeah, exactly. Fourth, the manufacturing controls on the factory floor, the PFMEA. And finally, the design verification plan and report, the DVP and R, which are essentially the physical torture tests.
Okay, let's unpack this. Let's start with the root cause. Before we can explore how the system saves the car, we have to understand the exact physical mechanisms of how the motor tries to destroy itself.
Right.
We're talking about a permanent magnet synchronous motor and a stator winding short circuit. This means the copper wires coiled inside the motor short out against each other or against the metal casing.
Yeah, the stator windings.
And the document refers to this as a highly destructive hardware failure, but it doesn't just happen randomly, right? The breakdown is like a cascading failure matrix driven by 4 distinct physical factors.
Yeah, it's not just one thing going wrong. The first of those factors is thermal degradation.
So heat.
Massive heat. When you execute a full throttle acceleration or sustain heavy torque while towing up a hill, massive phase currents flow through those stator windings. This triggers localized dual heating, which is mathematically represented as I squared R.
Okay, I squared R, current squared times resistance. So if you double the current to get more torque, the heat generated doesn't just double, it quadruples.
Exactly, it's exponential. And copper has a positive temperature coefficient, meaning as it gets hotter, its resistance actually increases.
Wait, so the hotter it gets, the more it resists, which generates even more heat.
Yes, exactly. It's a feedback loop. And if the cooling medium, like the oil or water glycol mix, isn't carrying that heat away fast enough, the motor hits thermal saturation temperatures frequently exceeding 130 to 150 degrees Celsius.
Man, and it isn't just sitting at that temperature, right? It's thermal cycling. Like you
Yeah.
park the car outside in winter, it drops to minus 40 degrees Celsius, and then you merge onto the highway and it shoots up to 150 degrees.
That cycling is brutal. I mean, it's brutal on the polymer enamel.
Right, because the wires aren't just bare metal.
No, the copper wires in the stator aren't wrapped in thick plastic like a household extension cord. They are coated in a microscopic layer of paint-like polymer enamel.
Ah.
And under constant extreme thermal stress, the long molecular chains in that polymer begin to break down. The enamel undergoes irreversible thermal aging.
It gets old fast.
Yeah, it loses its flexibility, becomes brittle, and its dielectric strength, which is its ability to block electrical current, massively degrades.
Okay, so the foundation is weakened by heat. That sets us up for the second factor, which frankly sounds like a localized thunderstorm inside the motor.
It really does.
Partial discharge caused by silicon carbide or SiC components. Now, silicon carbide is the darling of the modern EV world because it's so efficient. But that efficiency comes with a massive penalty, doesn't it?
It does. I mean, silicon carbide power modules allow us to reduce switching losses because they can turn on and off at blistering speeds compared to traditional silicon IGBTs.
Right.
But that high-frequency switching creates an extreme rate of voltage rise over time, which engineers denote as DVDT. We are talking about voltage spikes exceeding 10 kilovolts per microsecond.
10 kilovolts in a microsecond. To put that in perspective, a standard wall outlet takes a full 16 milliseconds just to cycle 120 volts. How is a microscopic layer of baked enamel not instantly vaporized by a 10,000 volt spike in a millionth of a second?
Well, the voltage isn't 10,000 volts in absolute terms. It's the rate of change that is 10 kilovolts per microsecond.
Oh, I see. It's the steepness of the wave.
Exactly. But when a voltage wave moves that incredibly fast down the cable from the inverter to the motor, it encounters the parasitic inductance of the stator coils. Because the wave is so steep, it doesn't distribute evenly across all the windings. It slams into the first few turns of the wire like a wave hitting a breakwater.
Wow, okay.
You get a transmission line reflection effect, which can actually double the voltage right at the terminals.
So the very first loop of copper wire takes a massive, disproportionate voltage strike.
Yes. And when that localized transient voltage exceeds the ionization threshold of the microscopic air gaps trapped between the wires, it triggers a partial discharge.
A spark.
Basically. According to Paschen's law, at certain small gap distances, the electrical field is strong enough to rip electrons right off the air molecules, turning the air into a conductive plasma.
Wait, plasma? Inside the motor.
Tiny plasma arcs, yeah. And this tiny electrical arc releases extreme localized heat and ozone. The ozone is highly reactive and literally oxidizes and burns right through whatever is left of that thermally degraded enamel layer we just talked about.
That is insane. So the heat bakes the insulation until it's brittle, and the high-speed silicon carbide switches create plasma arcs that burn holes right through it. Which brings us to the third mechanism, mechanical wear. The motor is experiencing high-frequency mechanical resonance, right? Like typically between 100 hertz and 1,000 hertz.
Yeah, and you have to add to that the harsh shock and vibration from the road surface, potholes, gravel, speed bumps. Plus, there are Lorentz forces at play.
Lorentz forces, remind me what that is.
When you push massive current through a wire in a magnetic field, the wire physically tries to move, so the wires are actively vibrating against each other thousands of times a second.
And because the enamel is already baked and blasted with plasma, this micrometer-level rubbing acts like sandpaper. It just physically scrapes the insulation away, exposing the bare metal copper.
Which leaves the door wide open for the fourth factor,
Right.
electrochemical migration. This occurs when the external environment invades the motor housing. Over time, rubber O-rings and seals degrade.
They dry out or crack.
Exactly. And if they fail, moisture, condensation, road salt, or cooling oil, contaminated with microscopic metal shadings from the transmission, can enter the stator chamber.
Okay, so assuming you have a bare patch of copper wire exposed because of the sanding effect, what happens when that moisture hits it in a high-voltage environment?
It triggers a rapid electrochemical reaction. In the presence of a strong electric field and an electrolyte like, say, salty condensation, metallic ions actually migrate from the anode to the cathode. The metal literally dissolves and replates itself, growing microscopic metal dendrites.
The sources describe these dendrites as looking like tiny metallic trees or weeds under a microscope.
That's highly accurate, actually. These tiny metal branches grow across the microscopic gap between two adjacent wires. Once they bridge that gap, They create a low-impedance conductive pathway, and the moment that happens, boom, you have a direct, fatal phase-to-phase or phase-to-ground short circuit.
Okay, let's unpack this for a second. If we know that the extreme dB/dt switching of silicon carbide and the intense heat are so incredibly destructive to the internal materials, why did the industry move away from traditional silicon? Like, why not just stick to the older, slower electronics, keep the voltage lower, and save the hardware?
What's fascinating here is the absolute limit of traditional materials. Consumers demand hyper-efficiency. They want an EV that can accelerate aggressively, tow heavy loads, and still deliver 400 miles of range.
Right, everyone wants more range.
And traditional silicon IGBTs simply lose too much energy as heat during switching. To get the required efficiency and range, you have to move to wide bandgap semiconductors like silicon carbide. The engineering challenge isn't to remove the stress, it's to design a system capable of surviving it.
Survive the storm, basically. Which brings us perfectly to our second dimension, the 60-millisecond race. We understand the physical mechanisms of the short circuit now. So how does the system fight back? We're moving from the physical breakdown to the digital defense mechanism, exploring that ASIL-D requirement of a 60-millisecond response time.
Right, to manage this, the power control system relies on a highly synchronized co-diagnostic defense line. It is split between ultra-fast hardware protection, which acts as a reflex, and complex software algorithms, which act as the brain. And it all starts at the hardware chip level.
Okay, the document mentions chip-level hardware protection and specifically talks about DESAT, or desaturation monitoring. Let's walk through the exact microsecond a short circuit occurs. The dendrite bridges the gap, where the wires finally rub together. What actually happens?
The moment a severe short circuit happens, the electrical resistance drops to nearly zero. This triggers a massive instantaneous shoot-through current that hits the inverter bridge arms.
A shoot-through current.
Yeah, and if this is allowed to flow for even a fraction of a millisecond, it will instantly exceed the thermal limits of the silicon carbide modules and literally melt them into a block of slag.
So the main computer doesn't have time to process this. Like, it can't run a diagnostic check.
Exactly. The central microcontroller unit, the MCU, is simply too slow. To combat this, the system uses smart, isolated gate driver chips located directly on the power modules.
Ah, okay. Decentralized brains.
Yes. Our sources name specific components like the UCC5880Q1 or the MC33GD31XX. These chips have built-in extreme speed desaturation monitoring. Right. In a normal state, when a transistor is fully on and saturated, the voltage drop across it is very low. But when a massive short-circuit current spikes, the transistor pulls out of saturation and the voltage across it suddenly spikes.
So the chip monitors that specific voltage drop, and if it spikes, it knows a short has occurred. And it reacts in 1 to 2 microseconds. A microsecond is a millionth of a second. But the source material notes it executes a two-stage turnoff. Why 2 stages? If a massive current is about to melt the inverter, why wouldn't the chip just slam the door shut instantly?
Because of Faraday's law of induction.
Okay, physics time.
Right. If you shut off a massive current instantly, you create a massive rate of current change, or ID. The power cables and internal bus bars have parasitic inductance. An instantaneous drop in current will induce an electromotive force, a massive overvoltage spike that would blast right through the silicon carbide modules anyway. You'd save it from the current but destroy it with voltage.
Ugh. It's like a water hammer effect in plumbing. Like, if water is rushing through a pipe and you slam the valve shut instantly, the kinetic energy of the water has nowhere to go and it bursts the pipe. You have to close it slightly slower to let the pressure dissipate.
That is a brilliant analogy, yes.
Yeah.
The two-stage slow shutoff intentionally drops the gate voltage in a stepped manner, safely choking off the current without generating a fatal overvoltage spike.
Smart.
And while it's doing this autonomous reflex shutdown, it uses an isolated safety channel to alert the main MCU in under 100 microseconds.
So the hardware acts as the reflex, pulling your hand away from the hot stove in a microsecond. But then the brain, the software, has to figure out what just happened. The sources detail 2 major software diagnostics that take over. The first is the KCL residual monitor.
Yes, KCL stands for Kirchhoff's current law. It states that the total current entering a junction must equal the total current leaving it.
Basic physics, yep.
The software, constantly, in real time, monitors the currents of the 3 phases of the motor, phase A, phase B, and phase C. In a balanced 3-phase system, the instantaneous sum of EA plus E plus EC must equal exactly 0.
Because the current is just circulating back and forth between the phases, so the net sum is 0?
Correct. The software calculates this sum continuously. If one of the motor windings shorts to the metal casing, a ground fault, Some of that current leaks away into the chassis. Suddenly, the balance is broken. The sum severely deviates from zero.
And it catches it.
The algorithm identifies this residual common mode imbalance and diagnoses a ground fault in less than 2 milliseconds.
It's like a nightclub bouncer counting people going in and out of the front door. If 10 people go into the club and only 9 come out at closing time, the bouncer knows instantly that one person is hiding somewhere inside. The math has to balance.
Exactly. But KCL only works if current leaves the system. What if the short is just a minor turn-to-turn short? Just one loop of wire touching the loop immediately next to it.
Oh, right, because no current leaks to the ground, so the KCL sum still equals 0.
Right. And the overall current hasn't spiked high enough to trigger the 1 microsecond hardware deset reflex either.
So the bouncer wouldn't notice because no one left the club. They just moved to a different table inside. How does the software catch a highly localized internal fault before it cascades into a total failure?
This is where we get into complex mathematics. The software uses symmetrical components analysis, specifically extracting the negative sequence current.
Negative sequence current? What's that?
In a healthy motor, the magnetic fields are perfectly symmetrical and rotate smoothly. But when a minor turn-to-turn short happens, it subtly disrupts that symmetry. The software runs a background decoupling matrix, often utilizing Clark and Park transformations, to translate the three-phase currents into a rotating DQ coordinate system.
Okay, you're losing me a bit. What does that mean in simple terms?
It basically separates the current into a positive sequence, which rotates forward with the motor, and a negative sequence, which essentially represents an unbalanced magnetic field rotating backward.
Oh, it's like listening to a symphony orchestra, and one violin is out of tune. Even though the overall volume of the music hasn't changed, the harmony gets warped. If the system detects that backward rotating negative sequence reaching a specific threshold, it knows a turn-to-turn short is developing.
Exactly, the off-key violin.
Mm.
And once the software, either through the KCL bouncer or the negative sequence extraction, confirms a severe short, we hit the most critical phase, the safe fallback.
Okay, right.
The system has to transition to a safe state to prevent the high-voltage battery from continuously pumping energy into the short and causing a fire, while also keeping the car dynamically stable on the road. And it has to finish all of this before our 60-millisecond window closes.
Right, and the appropriate reaction depends entirely on the speed of the vehicle. The document says if you are at low speeds under 20 kilometers per hour, the system executes three-phase freewheeling. It just completely blocks all the gate signals in the inverter, the electromagnetic torque drops to 0, and the car safely coasts to a stop. That makes intuitive sense. But at high speeds, over 80 kilometers per hour, it says simply cutting power is deadly. Wait, let me push back on this.
Sure.
If I'm doing 80 on the highway and the motor experiences a catastrophic short, my instinct is to sever the connection to the battery immediately. Isn't opening the circuit the absolute safest way to prevent a battery fire?
It feels incredibly counterintuitive, but in the realm of electromagnetism, simply opening the circuit at high speed is a disaster. If you cut the power, you trigger uncontrolled generation, or UCG.
Uncontrolled generation.
Yeah. The vehicle has mass and momentum, meaning the wheels are forcibly spinning the motor at thousands of RPM. A spinning permanent magnet motor acts as a massive generator. The permanent magnets on the rotor are sweeping past the stator coils, inducing a massive back electromotive force, or back EMF.
So the motor goes rogue. It stops being an engine and becomes a high-voltage generator pumping out juice.
Yes. And because the inverter switches are all turned off, that high-voltage back EMF will rectify through the anti-parallel diodes inside the silicon carbide modules, violently pushing power backward into the DC bus.
Oh, wow.
This uncontrolled voltage will rapidly exceed the limits of the electrical architecture, blowing up the capacitors and potentially overcharging and combusting the high-voltage battery.
Okay, so you absolutely cannot leave the circuit open because uncontrolled generation blows up the battery. So logically, why not just short all three phases of the motor together instantly? Just lock it down electrically so the voltage drops to 0 and it can't generate power back to the battery.
Because if you do a direct, immediate, three-phase active short circuit in ASC, you hit another wall of physics. When a motor is spinning at high speed and you instantly short all the terminals together, the massive back EMF drives an astronomical transient current strictly within the motor windings.
Okay.
This colossal current creates an opposing magnetic field that hits the rotor like a sledgehammer.
A magnetic sledgehammer, what does that actually do to the physical components?
It creates a massive transient demagnetization field. The rate and severity of this shock are determined by the armature time constant, mathematically represented as tau sub A, which equals 2 LD times LQ over RS times the sum of LD and LQ.
Hold on, let's break that formula down so we aren't just swimming in alphabet soup. What do those variables actually mean in the real world?
Fair point.
Mm.
LD and LQ represent the direct axis and quadrature axis inductance of the motor. You can think of inductance as electrical momentum, the current's resistance to changing direction. RS is the stator resistance. So this formula dictates how long the massive asymmetrical transient current takes to decay.
Okay, and if you short it instantly.
If you hit that high-speed motor with an instantaneous short, the transient current spike will permanently wipe the magnetic fields off the permanent magnet.
It literally erases the magnets.
It does. Furthermore, that transient electrical spike translates into a sudden, violent jerk of negative mechanical torque, which can literally snap the axle or shatter the mechanical transmission gears.
So you are completely boxed in by physics. You can't leave the circuit open because uncontrolled generation blows up the battery. You can't shut it down instantly because the transient demagnetization current snaps the axle or erases the magnets. So what is the solution? How do you defuse the bomb?
The solution is an incredibly elegant mechanical ballet called the stepwise active short circuit, or stepwise ASC. It's a precisely timed, two-stage process designed to thread the needle between those two catastrophic extremes.
Okay, so you have the motor howling at highway speeds, the short is detected, and the 60-millisecond clock is ticking. What is stage one?
The moment the fault is confirmed, the system dynamically calculates the optimal switch combination and executes a two-phase short circuit, a 2PSC.
Just two phases.
Right, by only shorting two phases instead of three, it acts as a transitionary step. It suppresses the initial runaway voltage on the uncontrolled generation, but it doesn't create the massive sledgehammer effect of a full three-phase short. Then the system waits. It intentionally delays the next step for exactly 1.5 milliseconds.
Why exactly 1.5 milliseconds? What is physically happening inside the motor during that delay?
That precise 1.5 millisecond window allows the asymmetrical transient DC component of the short circuit current, governed by that armature time constant formula we just discussed, to naturally decay through the stator resistance. It is mathematically calculated to let the peak demagnetization current and the maximum torque spike pass harmlessly.
It's letting the kinetic energy of the fault burn itself out.
Exactly. Once that transient spike is safely decayed, the system triggers stage two. It shifts into a three-phase short-circuit lower switch state, or 3-PSLS.
And that does what?
It turns on all the lower switches in the inverter. This safely clamps the DC bus voltage strictly under 720 volts, protecting the battery and power electronics, while resulting in a smooth, manageable negative torque that gracefully slows the car down.
And if we step back, the 1 microsecond hardware desat reflex, the KCL software bouncer counting the current, the negative sequence matrix detecting the asymmetrical fields, the two-phase short, the 1.5 millisecond dodge, and the final three-phase clamp. All of that happens entirely autonomously in less than 60 milliseconds.
Yes, the system detects a failure, calculates the physics, and executes the fallback before your brain can even process that you heard a noise.
That is genuinely incredible engineering, but catching a failure in 60 milliseconds is a massive feat. Yet, having to use that safety net means something structurally broke, right?
Yeah.
A dendrite grew or the enamel failed.
Right, the root cause occurred.
Exactly. So how do engineers design the motor so it doesn't break in the first place? This brings us to the third dimension, design failure mode and effects analysis, or DFMEA.
The best safety system is the one you never have to trigger. In the DFMEA phase, engineers mandate critical physical protective controls to block the electrical, thermal, and mechanical stresses we talked about during the root cause analysis.
Right. And earlier we discussed the 4 physical breakdown mechanisms: the baking heat, the mechanical vibration, the tiny lightning bolts of partial discharge, and the metal weeds, the dendrites. How does the physical design directly counter the laws of thermodynamics trying to destroy the motor?
Let's start with the wire itself. To fight those high-frequency DV/DT lightning bolts, the partial discharge caused by the silicon carbide switches, the design mandates the use of corona-resistant enameled wire.
Corona-resistant. What makes it corona-resistant compared to normal copper wire?
It features a highly specialized 3-layer co-extruded structure.
3 layers, okay.
The base layer provides strong adhesion to the copper. The middle layer provides high dielectric strength, but the top layer is the key. It is doped with inorganic nanoparticles, often silica or alumina.
Nanoparticles.
Yeah, when a partial discharge plasma arc hits that wire, the organic polymer might erode, But those inorganic nanoparticles act like a microscopic shield, massively resisting the high-frequency electron bombardment.
So it physically blocks the plasma from chewing through. What about the intense thermal degradation, the joule heating?
That specialized wire is strictly locked into a Class N insulation rating. In electrical engineering, insulation classes dictate the maximum continuous operating temperature. Class N means it is rated for a continuous operating junction temperature of 200 degrees Celsius.
Wow, 200
Yeah,
degrees.
this massively boosts its thermal fatigue endurance limit, preventing the polymer chains from breaking down during that extreme winter to summer thermal cycling.
Okay, so we have nanoparticle shielded heat-resistant superwire. But what about the mechanical scraping from the 1000 hertz vibrations?
The engineers design physical, rigid barriers. Inside the stator slots, where the wire is packed tightly against the steel core, the design demands the use of a three-layer, highly tear-resistant dielectric insulation paper, usually a composite like Nomex Captain, known as a slot liner.
A slot liner.
Right. Furthermore, at the winding ends, the end turns where the physical routing forces the different phases to cross over each other, they use dedicated phase insulation paper.
So they are weaving armor between the wires.
Exactly. It guarantees absolute physical isolation between the three phases. So even under intense random vibration and Lorentz forces, the wires from phase A can never physically vibrate against the wires from phase B and scrape each other raw.
So the motor is physically armored. But what about the electronics? If a short does happen, how do they protect the delicate, low-voltage computer brain of the car from being fried by a massive high-voltage surge?
To prevent electrical overstress, or EOS, from propagating back into the logic board, the DFMEA dictates that the isolated gate driver chips must have a common mode transient immunity, or CMTI, of greater than 100 kilovolts per microsecond.
Meaning the microchip has an isolation barrier so robust it can shrug off a 100 kilovolt noise spike without letting a single false signal pass through to the main computer.
Correct. But they also have to protect the power modules from themselves. The driver circuit incorporates a negative gate bias, typically holding the gate at -5 volts when off, and an active Miller clamp, an AMC mechanism.
Explain the active Miller clamp. What is the Miller effect?
Inside every transistor, like a silicon carbide MOSFET, there is a tiny, unavoidable parasitic capacitance between the gate and the drain. When one switch in the inverter turns on very rapidly, it creates a massive DVDT voltage spike.
Okay.
That high-speed voltage transient can couple through that parasitic Miller capacitor into the opposite switch that is supposed to be off. It basically forces current into the gate, pulling the gate voltage up. If it pulls it above the threshold, that bottom switch accidentally turns on.
Oh, I see. And if the top switch is on and the bottom switch accidentally turns on at the same time, you have a direct short circuit straight through the inverter to the ground.
Exactly, a fatal shoot-through. The active Miller clamp is a dedicated physical circuit that actively monitors the gate voltage. When the switch is supposed to be off, the AMC physically shorts the gate directly to the negative ground, providing a low impedance path to bypass that parasitic Miller current. It physically clamps the door shut so the high-speed transient cannot force it open.
So we have an absolute fortress. The blueprints are flawless. We have Class N nanoparticle wire, tear-resistant composite paper, and microchips with 100 kilovolt shields and active Miller clamps holding the doors shut.
On paper, yes.
Right, which brings us to the fourth dimension. Process failure mode and effects analysis, or PFMEA, because a theoretical fortress is useless if the factory botches the assembly. If a robotic arm twitches a millimeter too far to the left and scratches that enamel, all that 100 kilovolt protection is useless. How do they physically manufacture this without a single microabrasion?
Manufacturing at this level of precision is arguably as complex as the electromagnetic physics. You absolutely cannot rely on human hands to wind these stators. The process controls are draconian.
The document details automated assembly and sealing. It mentions automated needle winding. How does that prevent damage?
To prevent artificial abrasion to that highly engineered enamel layer, the winding process is fully automated using high-speed needle winding with closed-loop tension control. A robotic arm moves a needle to thread the wire into the stator slots.
Makes sense.
The copper wire stretches if you pull it too hard, which thins out the insulation. The closed-loop tensioners monitor the exact pulling force in real time, dynamically adjusting the tension thousands of times a minute.
So it packs the wire perfectly tight against the steel core, ensuring maximum electromagnetic density without a single micro-collision or overstretch that could weaken the insulation.
Precisely. And once the physical winding is complete, it has to be locked into place to prevent the vibration damage we discussed earlier. It goes through vacuum pressure impregnation, or VPI, followed by epoxy encapsulation.
Walk me through the physics of VPI. Why not just dip it in epoxy and let it dry?
Because dipping leaves air. In VPI, the entire stator assembly is placed into a chamber, and a massive vacuum is pulled, sucking every molecule of air out from inside the microscopic crevices between the tightly wound wires. Then, highly thermally conductive epoxy resin is flooded into the chamber, and the pressure is reversed, driving the resin deep into the windings via capillary action.
And what happens if the vacuum isn't perfect and a tiny bubble of air remains trapped in the epoxy?
A bubble is catastrophic. After the resin cures, the factory uses 3D automated optical inspection, or AOI, to guarantee a 100% fill rate.
Okay.
If there's a microscopic void, a bubble, it means trapped air. In a high-voltage environment driven by silicon carbide, that trapped air pocket has a lower dielectric constant than the surrounding epoxy. The electric field concentrates inside that bubble, ionizing the gas and creating a persistent internal partial discharge.
A tiny plasma storm trapped inside an epoxy bubble, slowly chewing its way out until it causes a short.
Exactly.
Okay.
So the vacuum and the AOI ensure absolute zero voids. But they don't stop there. We move to the inline testing. Before the motor ever leaves the assembly line, they hit it with a 100% surge test.
What are they looking for with a surge test?
They fire high-voltage pulses directly into the coils to create an LC resonant circuit, and they analyze the electromagnetic waveform decay signature. If there is even a microscopic turn-to-turn short the optical inspection couldn't see, the resonant frequency and the damping of the waveform will degrade slightly compared to a master signature.
So they compare it to a perfect model.
Right. The automated machine catches the deviation and scraps the motor. They also perform inline partial discharge testing to weed out any motor that shows a hint of electrical corona under maximum working voltage.
And finally, we have to solve the fourth mechanism of failure from our root cause analysis: electrochemical migration, keeping a salt water and the metal shavings out. The source specifically mandates dual-stage, high-precision helium leakage testing. Now, why helium? Why not just pressurize the motor with air and dunk it in a water tank to see if bubbles come out, like checking a punctured bicycle tire?
It comes down to atomic radii. A water molecule is approximately 275 picometers wide. Oil molecules are even larger. A helium atom is only 32 picometers wide. It is one of the smallest, most penetrating gases in the universe.
Huh.
During this test, the motor is placed in a vacuum chamber, pressurized internally with helium, and mass spectrometers sniff for escaping atoms.
So if the sensors detect absolutely zero helium escaping from the O-rings and connectors, it means the seal is perfectly tight at a submicroscopic level.
Exactly. If a 32 picometer helium atom can't squeeze out of the seals, a 275 picometer water molecule or a massive droplet of transmission fluid definitely cannot get in. It completely breaks the chain of failure required for dendrite growth.
Okay, so we've mapped the failure. We've designed a theoretical 60 millisecond digital shield and a physical nanoparticle fortress. We've built it flawlessly with automated tensioners, vacuum epoxy, and helium leak testing. Now, what do the engineers do before they let the public drive this? This brings us to our fifth and final dimension: the DVP and R validation, design verification plan and report. This is where they basically try their absolute hardest to destroy their own creation.
They leave nothing to theory. The environmental and endurance tests are brutal. Let's look at the high-frequency DVDT thermal vibration combined endurance test.
Just the name of that test is intimidating. What exactly does it entail?
They mount the fully assembled motor onto a specialized rig and subject it to 3-axis random vibration from 10 to 2000 hertz, pulling an acceleration of 35 meters per second squared.
So they are violently shaking it in every direction to simulate the absolute worst-case Lorentz forces and road shock.
Yes, but while shaking it, they put the entire rig inside an environmental chamber and slam the ambient temperature back and forth from minus 40 degrees Celsius to plus 150 degrees Celsius.
Shaking it while simultaneously freezing and baking it to force thermal expansion and contraction on the epoxy and wire.
And while it is shaking, freezing, and baking, they powered up using the actual silicon carbide drive, hitting those windings continuously with those 10 kilovolts per microsecond voltage spikes. And they sustain this combined torture continuously for over 500 hours.
500 hours of continuous abuse. What is the passing grade for a test like that? How do they know it actually survived?
They tear the motor down and inspect it. There must be 0 micro cracks in the enamel. The contact resistance of the phases cannot have shifted by more than 1.2 millions. And crucially, The partial discharge inception voltage, the PDIV, must be remeasured and remain safely above 1.5 times the peak back EMF and switching surge voltage. Meaning, even after 500 hours of mechanical and thermal aging, the insulation still will not allow a plasma arc to form.
That is wild. And what about the environmental sealing? How do they prove the helium test actually translates to the real world? The document mentions an IP69K test.
The IP69K test is the ultimate intrusion standard. They take the motor and subject it to 96 hours of constant, highly corrosive neutral salt spray to attack the metals and seals. Immediately after, they hit it with a high-temperature, high-pressure water blaster. We're talking 80 degrees Celsius water at 100 bar of pressure, sprayed from every angle.
Like a supercharged, boiling pressure washer point blank on the seals.
Exactly. After surviving the salt spray and the pressure washing, they connect a high-voltage digital megahometer and hit the internal phase wires with 500 volts DC for 60 seconds.
To see if any moisture got inside and compromised the insulation?
Precisely. The insulation resistance must measure greater than or equal to 100 megohms, with absolutely zero microamp leakage to the ground. Then they tear the motor completely apart to physically prove there is 100% zero oil or moisture ingress inside the stator chamber.
The helium test proven right in the most brutal way possible. But all of that, the 500 hours of shaking, the boiling pressure washers, that is just the warm-up for the final exam. The HIL, or hardware in the loop, short circuit injection.
This is where everything we've talked about today converges. They mount the motor on a dynamic dynamometer testbed. They power it up and spin the motor to a screaming 12,000 RPM under maximum continuous load.
12,000 RPM. The mechanical inertia in that rotor is massive. If something goes wrong at that speed, the motor could physically tear itself off the testbed.
It absolutely could. And while it's howling at full load, they use a specialized hardware fault injection card. This is a massive external IGBT-based circuit designed to intentionally and instantaneously trigger a massive phase-to-phase or turn-to-turn metallic short circuit directly into the motor terminals.
So you have a motor howling at 12,000 RPM. If you inject a short circuit now, you're essentially recreating that uncontrolled generation nightmare we talked about earlier. The system has to execute that 1.5 millisecond mechanical ballet perfectly, or the test cell essentially blows up, right? I am marveling at the absolute confidence these engineers must have to intentionally short a motor spinning at 12,000 RPM just to prove a point.
They have to prove the software and hardware integration works in reality, not just in a simulation. The acceptance criteria for this final test are rigid and binary. The hardware DISAT monitor must detect the massive current and execute the two-stage slow shutoff in 1 to 2 microseconds. The safety management software must recognize the fault, calculate the parameters, and execute the stepwise active short circuit in less than 60 milliseconds.
The system has to catch a live grenade, disarm it, and set it down gently, all in a fraction of a blink.
And we measure the aftermath. The transient DC bus voltage must be recorded clamping safely below 720 volts. And after the dynamic forces bring the motor to a halt, they dismantle it. There must be 0% demagnetization of the permanent magnets, and there must be absolutely zero secondary physical burning or electrical overstress damage to the logic boards.
It has to survive perfectly every single time, or the design doesn't go to production.
It is the ultimate validation of everything from the atomic structure of the wire enamel to the microsecond response time of the code.
So what does this all mean for you, the listener? We've gone on a deeply technical journey today. We started with the microscopic villains, the extreme I²R heat baking the polymer chains, the tiny silicon carbide plasma lightning bolts, the Lorentz force mechanical scraping, and those terrifying microscopic metal dendrites growing in the dark.
Yeah, it's a harsh environment.
We watched the system fight back, using a 1 microsecond hardware reflex and the brilliant KCL software bouncer. We unpacked the complex physics of uncontrolled generation versus demagnetization and witnessed the 60 millisecond mechanical ballet of the stepwise ASC, waiting that precise 1.5 milliseconds to dodge the torque spike and save the vehicle. We explored the impenetrable physical fortress of Class N wire, vacuum-sealed resin, and active Miller clamps. And finally, we watched the motor survive a 12,000 RPM intentional sabotage on a test stand.
It really highlights that true mastery of a subject means intimately understanding what happens when absolutely everything goes wrong and engineering backward from that absolute worst-case scenario. And I want to leave you with a fascinating final nugget mentioned in our sources regarding the development of this system.
Oh, what's that?
We spent a lot of time analyzing how the engineers designed that exact 1.5 millisecond delay for the stepwise ASC fallback to dodge the tau sub at demagnetization spike. To even conceptualize and calculate that, they don't just guess or build endless physical prototypes. They use advanced Python simulation tools.
Of course they use Python. It always comes back to Python.
Always. They use Python to build a hyper-complex dynamic model of the transient asymmetrical short-circuit electromagnetic torque and demagnetization characteristics. They mathematically simulate the failure millions of times before they ever build the first copper wire. But think about what that means in a practical sense. Next time you see an EV silently gliding down the highway, looking so calm, simple, and serene, realize that behind that quiet exterior, there is a digital brain constantly running these hyper-complex physics algorithms. It is monitoring the balance of electricity at a microsecond level, armed with 100 kilovolt shields, ready to execute a mathematical mechanical ballet to save the car the exact millisecond chaos strikes.
You know, at the very beginning of this, I thought about how a flat tire on a traditional car is a problem you can see and understand. It's visible. But after diving into the sheer scale of the engineering required to manage this invisible 60 millisecond electrical war zone, I think I prefer the invisible shield. The level of human ingenuity dedicated to keeping us safe at speeds we can't even comprehend is truly staggering.
It is a testament to modern engineering.
Thank you for joining us on this deep dive. Go mull over those Python simulations, and we'll catch you next time.